Right, episode 20. So you're welcome back. I know it's been ages, but here we are. It is what it is. Um, just been very busy with work and with Formula One stuff. Doing a lot of track support now for the V10s and keeping an eye on things and engine rebuilds or problems with various Formula One cars. So that's taking up a bit of time traveling through Europe and diagnosing problems or looking at cars or keeping an eye on the racing and all that. But I thought it was important to get out something. So I've had these parts on hand. Now, originally I'd intended doing this video on a V10 parts, but these are Cosworth CA V8 parts, which are nearly identical to the V10 parts. Now, I had to get rid of the V10 parts about, 4 or 5 days ago, just for an engine rebuild. But these are the V8 parts, so they're pretty similar. In terms of dimensions and all that, they were kind of the same, the V10 and the V8. In terms of size, fit and finish, all that sort of thing, it's pretty much the same. So let's have a look at these. So yeah, I hope you enjoyed your summer, by the way. As you know, I'm from Ireland here. We had, I think, about 2.5 weeks of sunshine. So that was fairly terrible. Out of 3 months, but you can probably hear it in the camera now. It's raining here now again, so it's just been a disaster. As some of you know, I've bought a new bike as well during the summer, a K1300R, which would be a rare bike here. It's an inline 4-cylinder, 173 horsepower, quick shift and all that. I think top speed is like bonkers. I don't know what it is, 180 or 200 miles an hour. But a very rare machine here, and I've been out in it about 4 times, so that's how bad it's been. But a nice machine. But yeah, I think that's probably it for the summer on that bike, because it's pretty highly strung. So I'll be back to the GS now for the winter. But yeah, the parts. All right. So these parts are from Cosworth, and you can still buy these parts new. I had a dig there on the community comments section of there's this guy. I don't know why, but he just annoys me so much. But I'm probably too old for that at 42. It's time to get over that, but he just has no idea what he's talking about. Like, I buy these parts or buy them for companies that want to fix up their engines or their cars, and I think he quoted a price of €50,000 for a piston. Even I know the guys in Red Bull now, and the pistons are nowhere near that. And it's just frustrating. I don't know why it is. I'm a long time on forums since I was about, since I got a computer, whatever it was. Oh, I don't even want to think how many years ago. But I know he's there for clickbait. I don't want to concentrate too much on it, but it's just like, it's bonkers what he's saying, So I can't even remember his name now. I wouldn't even mention it if I did remember it, but just ignore that guy. So this piston here is from the CAV8. There's a Conrod there as well from the CAV8. I think between them, this piston new is roughly €1,200, €1,300. The Conrod is about 800. The rings are about 200 quid a set, or each. The bolts, I can't remember, €80. The pins, €80 each. The small end pin, €80. So unless he's dividing the cost of the parts from the R&D phase all the way down, top down, accounting, it's just laughable. But anyway, let's ignore all that. So yeah, I spoke before about, briefly, well, not briefly, but kind of in depth, in terms of tolerances and, small end, big end, bore tolerances and all that sort of thing. I don't really want to get into that too much because it doesn't matter awfully much. We all know that a Formula One engine by now isn't seized when it's together and built when cold. That's nonsense. So put that out of your head. There is a tolerance there on the the big end here, I think it's about 35 microns. And on the piston bore, it's fairly standard. I can't remember off the top of my head what it is, but everything can turn. So that's one myth to be dispelled. But so where will we start? Let's start the Conrod, lower down. So this is the Conrod from the CA. So there it is there. Anyone that has never seen or has been lucky enough to see or hold or whatever, or buy or purchase an F1 Conrod, is the first thing you'll notice is they're tiny. So if I just keep it in camera there, so this would be a bog standard Conrod, which you're all familiar with. It'll be like if you were building a whatever, I don't know, I can't remember what this is off. Now this is steel, that's the only thing. I think it was off possibly WRC rally car, possibly Top Fuel Dragster, possibly NASCAR. I can't remember. There's a lot of stuff going through here. I see a lot of stuff. I don't claim to be an engine builder, by the way. My engine building history is, vintage lawnmowers from about 100 years ago. That's what my hobby is, or high fidelity stuff. There's really no in between. I've built a few Volkswagen engines for myself, high power GTI, Mark II GTIs, G60s, 16 valve G60s, but I don't for 1 second pretend to be a connoisseur on engine building. I'm at the very low end 100 years ago, or at the higher end to where we are now. So you've all seen a Conrod. So it's about what, center to center, 6.5 inches. So let's just pretend it's from a 2-liter GTI, Mark II GTI. So that's your standard Conrod, and this is an F1 Conrod. So you can see the difference. Like they're tiny, they're literally tiny. So center to center, as I said, this will be about 6 inches or 6.5 inches. This one here is, I think, 112 mil center to center. So 4 3/8 for all you American guys. This is titanium. The difference between this Conrod and this Conrod, which it's just a difference in these two, not in all Conrods. Like the side profile is roughly the same. They're that section there. I'm not going to say I-beam or H-beam because that'll start another row. Here we call these H-beam because it's like a H in cross section that way, but other people call them an I-beam. Looking at them this way, let's not get into that. This Conrod here, the F1 Conrod, has got no oil holes here, which this one has, so that might be a difference. It's got no axial relief oil holes here. As you can see, that's flat. This one has. I'm not saying this is every Conrod, I'm just saying the differences. The bolts are pretty much the same. The end caps, you can see yourself there. I'll let you judge what you want to think. The serrations are the same here. That's a Pankel thing. I actually passed by the Pankel plant when I was going by train to the Red Bull Ring, coming from Vienna, I think, to Spielberg. Pretty cool plant. Just saw it out of the window of the train, but very cool to see it. So I know they've got offices everywhere, but it was just nice to see the sign, and I got a picture, I think. But so yeah, so these will be forged blanks to get the rough shape and get the grain structure following in the metal. Same with the titanium. Obviously these would have more paperwork than these ones, because these aren't as highly strung. I think, let's guess, the top RPM of this rod here would be, let's say 10,000, whereas this would be I think tested or design tested to 21,000. Now I know there's a video on YouTube knocking around of the CA going to 20,000 on the dyno, I think, But I know from running the V10s in, where was the last place we were? In Assen, they can do 21,500. So, you know, they're well able. So again, just to compare these rods so that people are familiar with what's going on. The basic construction and method of fabrication or assembly is kind of the same. So these have a serrated edge here and here, which I'll show you more in a minute. The bolts are the same. The big ends are round, okay, so they're not oval as many people say, like this is oval because, or this one is oval because the engine gets, you know, such g-forces that it has to be oval this way, that when it's at maximum RPM it's in a circle. That's nonsense. This is round, as is the small end here. So let's put this one away. Just one more glance at the bolts there. They're all pretty similar here and here. So let's put that one away. So back to this rod here. The shells are in here. Again, the rod, I think 800 quid roughly. The shells are, I think, 150 or 160 or something like that. That's new now. These are new shells. This new rod. The bolts are new. I think they're about 40 quid each. They're made by Pankel as well in house. So just to open it up and show you. Now, if you're ever opening a rod that's serrated, a lot of people will know this. You open up the bolts to about 3 millimeters or 1/8 of an inch, and again to 1/8. So you can see the bolt is open there, and that one is open as well. And what you do then is you just pull the cap off like that. Let the bolts guide you, and then you can take them out. If you took out the bolts and then tried to take off the cap, you'll bend the pins that hold them together, which you will see in one moment. So let's get rid of these bolts. We can talk about them in a moment. Let's drop them down there carefully. So now you can see the serrations. So they're the serrations there, the sawtooth serrations. So they're axial in terms of you know, the engine crank center line or whatever. So what they do is just stop the big end cap from walking. So it just provides a nice interface. It also stops it from twisting this way too, a small bit. And again, there's the little dowels there. Now they're not roll pins. If you look at it really close, hopefully I can zoom, they're spiral pins. So they're more solid than a roll pin. They just tap in there to locate the cap. Now these will be ground like you would cut a gear. You know, nothing too special about that. Now there is, I think from memory, I've built a few Ducati engines for race bikes. There is a better crank interface than this. Now, getting back to interfaces, Pankel did an early interface which was just 2 pads with a relief in the middle, just to provide a higher pressure. You know, there was less surface area, so it was more pressure on them. But these are the later style cap. Now these were also present in the TJ engine, the V10, the serrated interface, because you've all seen them probably. Modern caps on engines are cracked, so that would be the cap, or the Conrod is all made like that. It's bored, it's ground, and then it's put into a machine which grips it here and here, and it's cracked off. And the crack is literally cracked off, so you can see a very jagged edge, and it has to mate together in anything like that, which provides a very detailed mating surface. But because this is titanium, you can't fracture crack titanium at all. It just doesn't want to do that. So that's why you have to go with this method here. Now, obviously, when this was machined, you'd machine it all. It'd be heat treated. It'd be checked. It'd be bored. and then it'll be shot peened. You can see the surface finish is really nice. You can probably see it there. I got new lights in the workshop lately, and they're terrible. They're LED lights, and it's impossible. Like, I know about LEDs and all that from the day job, but just the light from the ends of them, it's very directional. So if you can't see everything, it's because there was a load of new lights put up here, and they're terrible. But hopefully you could see what's going on there. Again, this bushing here is pressed in. Nothing fancy. Let's call it a silicon bronze bushing. They've been around for yonks. There's a lot of copper in that, just looking at the colour, but I'm not sure of the makeup. If anyone, I can find out the makeup if you want to know it, but it's just a bushing pressed in there. So let's pull out the shells. So again, if you're ever splitting a rod like this, if you can see, if I put it together like that, and try and split it, you've got a danger of, when you're doing that, there's a danger of bending those pins. So because this is a viable product or part, just to be sure, I'm going to put in these bolts again just to pin it, or just to pull it from the pins. So again, about 1/8 of an inch either side, or 3mm, pull that. That keeps the pull direction straight, and then you can remove the cap. So this is probably really boring to many of you that are just dealing with normal rods, but if you're dealing with high fidelity rods that have to go back, perfect, there's a lot of money on the back of an engine build sometimes. It just saves risk. So if we take out the shell, standard enough shell, taking out a shell again, push it sideways, and you can lift it out. So if we pull the shell out of this one, again, push it sideways and lift it out. So these shells, as mentioned, for a pair, they're roughly, I think, I can't remember. I said it a minute ago, but I can't remember now again. Let's say €150 for a set. They're nothing special. They're I think a two-piece material shell. So you've got a copper clad back, and then your leaded face. So hopefully we can zoom in, maybe, so you can see there you go. You can just see the soft face there. And I don't want to go too hard on this because this part is going into an engine, but it's really soft. So you can scrape it like that. And again, that's for any impurities in the oil that they'll just embed in there and not ruin the crankshaft. So the sizing of these bearings, if you're really sharp, you'd have noticed a blue mark here and here. So when Cosworth get these Conrods from Pankel, they come like that, and they come with a spec sheet. Now we also get that spec sheet when you're building the engine. So you've got this internal diameter here. So that would be a certain size. Let's just say, let's actually measure it. Hit the camera there, easy. So let's just say it's whatever it is, 37.33, okay? So Pankel will send with each Conrod, they're marked with a serial number, you get paper with the Conrod, what the exact bore is here, okay? So off that bore, you can then assign that Conrod to, let's say this is number 1. So that would be to throw number 1. So you assign that Conrod to throw number 1 on the crankshaft, okay? So you measure that journal diameter on the crankshaft. So that ideally is going to be 34 millimeters. That's what the spec calls for. But if it's not, if it's a little lower or a little higher, You would pick these shells then to provide 35 microns of clearance. Okay, so Cosworth did 8 sizes of these shells, depending on how near Pankel got their bore and Cosworth ground the crankshaft. Now, unlike, as I said, I'm not an engine, god or connoisseur. Um, with an F1 engine, you have to measure each journal, each Conrod, all along, and you treat each cylinder as its own entity, or whatever you want to call it. So each tolerance stack up is per cylinder. You don't measure, a big end and say, well, that's that, and then measure one of your Conrods. Like if you're doing up your whatever Honda or Golf, or your WRC car, you don't just pick one Conrod and go, yeah, that's it, that's fine, let's do all that for all of them. With an F1 engine, you measure each one individually. That also goes for this diameter here, or this length here, which will make up in the end your compression ratio. So every cylinder bank is measured all the way along, and it's put into a table. So this is a blue shell. You can just see a tiny bit of blue there. So that's done. You come up with, again, as many will be surprised, shock horror, all F1 engines that I've worked on, or that Cosworth recommends, they're sized with plastic gauge. Now, some of you might find that hilarious, but that's how it's done. Now, Cosworth do supply a machine to measure the thickness of these shells here, because these can vary as well, so you have to just basically measure everything. They also provide, the machine also measures the standoff height, or the crush height, which locks the bearing in the big end. So again, like, you could be picking from 100 or 200 shells to get the right one to get your tolerances, and that's kind of how that works. So is there anything else to say about the Conrod? The bowls, let's touch on the bowls. With Conrod design, especially this sort of Conrod, extremely high RPM and fracture issues, with the tension at top dead center. The most important area of a Conrod is here. If you're designing one, or you're looking at one, or one has failed, it's generally on a high-speed engine, it's generally that fillet there, right there. That's what's going to cause you problems. Obviously, if you've got everything, if in theory, if you've got this ginormous, very strong shape here, and that's all fine. This is huge here, that's all fine. It's generally that area there that's going to fail on you, where the last thread is, and that radius. So you want to have a good radius there. And I know for a fact Cosworth, Honda, Peugeot, a load of other teams spent a long time perfecting that radius there with Pankel, just to stop failures. As you can see, it's about 2 mil, and then again into the threads. It's just not an area to be ignored. So that is kind of that. Let's talk about the bolts. So with the bolts, a lot of you will know this, that are involved with aerospace or high fidelity engineering. These bolts are fairly standard. They're made by Pankel. They're a turned item. They're a wasted bolt, and they've got various features which you probably won't understand, but it's got to do with tension and stress risers and all that sort of thing. Now these have got a center there. You can see that, like they're turned on a lathe with the center drill, and on the other side. Now, a lot of people think these are, well, that's from manufacturer, that just casually see them, but they're not actually from manufacturer. They're for measuring the length of the bolt when it's torqued. So with any, high performance bolts, you get like a micrometer with 2 anvils here with 60-degree or 30-degree centers that locate in here. So before you put them in, you measure what's called the free length of the bolt. and it could be, let's just pretend it's 40 millimeters, and you would then enter the bolt, you torque it up, and you reference the torque sheet when they're in, tighten them all the way down, like that. So you've got your free unloaded length of the bolt, you torque it up, and on the engine build sheet you would have a new length of when it's torqued of what it elongates to. So that's why these are very precisionally ground there and there. So your micrometer anvil's located here when the engine is together. It's a very slim micrometer like that. So you would measure the stretch of the bolt and see what's going on there. And again, that will only be about like 0.1 or 0.15 millimeter, which should correspond to your torque values. And if they don't, there's something up, and you have to either, recheck or throw away the bolt. And when you've got that done, you record then, as you can see here. Hopefully I can get it. Just one sec. Yeah. So you can see the second part of that part number, which ends in 175F, is different to this one, which is 219F or something. I just can't see it in the camera, but you get the idea. Everything has an entry and a part number, and you have to be very careful putting stuff together. That's all. So yeah, I think that covers that. So I'm going to pause the video, move on to the piston, and then we'll put them together and have a chat about that. Right, so onto the piston. So as I said in the previous 25 minutes, whatever it was, this is a CA piston. So again, if you're used to pistons from motorbikes or from high fidelity whatevers, even outboard engines, this won't be too surprising to you. Now, if you're used to pistons from normal road cars, this is going to be a shock. As you can see, the skirt here on the side is non-existent. Even the skirt here on this side, it's pretty slim, but on the axial side, the skirt is non-existent. It's just about covers the bottom oil ring. Now, in terms of rings, on this piston, there's a compression ring here at the top, and there's an oil control ring here at the bottom. You should hopefully be able to see that in some direction. So you can see them both there. So on the top or the bottom of your screen is the compression ring, and on the bottom of your screen, compression ring, top of your screen is the oil control ring, and in between that is a groove, which Cosworth invented or came up with a long time ago, which basically controls flutter. It is to do with turbulence from the explosion not getting down to the oil ring or just dissipate it, so that it slows it down a bit. Again, you could write a whole thesis on pistons and on that groove or the groove shapes, but that's what that secondary groove is there. It's just very slight. You can hopefully see it there, but that's what it is. It's just let's call it a dampening path before the gases get to the oil control ring. So again, a forging, this piston is, I should know, I don't, 98. Yeah, 98. So 98 mil bore. You can see it's very pleasant to look at on the top. Again, this is from the right bank. So you've your intake valve cutouts here, your exhaust valve cutouts, and your squish zones here and here. So if we just turn it over, on the bottom, actually let's pull this pin. The temperature of the workshop now has gone down a bit, so this pin is a small bit hard to remove, but there she is. So the pin is steel. It's DLC coated, which is the diamond-like coating, vapor just deposition or depositation, whatever you want to call it. You can look up that DLC coating. It's nothing new. It's been around for a long time. I think it's even made its way into mountain bike or race bike gear sets now, so it's not as fancy as it once was. But the part will be ground, micro polished, and then coated, and then checked, obviously. Now, just to give you an idea, the pin diameter on this is 17.73. Now, that doesn't mean anything, but it just gives you an idea of the size. And the length is 42.47 on a terribly bad, very tired calipers, which I don't use for engine builds, but it's just one I had here to hand. But again, it's hollow. In the middle, there's like an 8mm hole. So that's the pin. Steel, probably the massiest or the heaviest part of the whole thing. Not heavier than the piston, but in terms of, you know, it just needs to be strong, but it's quite heavy because it's steel. So onto the piston. So again, not like your normal pistons. If you're used to just normal, you know, road car mechanic stuff. Like for example, the top total land and ring zones here is like 9.7 mil. These pads here were for machining it. You can see the little standoff pads here and here. So to be gripped here on the lathe and turned. Now, again, lightness is a huge thing with pistons. Like if you've got a Morris Minor or the most basic car ever and you want to make it quicker, the one thing I would say to you is get everything that's moving as light as possible and just keep your oiling in check. And obviously then onto that, because they're very light, you can spin them quicker. There's less pressure on your bearings, and spinning them quicker, you can get gases in or out quicker. So have your ports in shape. So it kind of, you know, it's like a waterfall, but just keeping everything light is pretty important. Stuff that's moving. Not to get hung up on it, but you know, again, your stroke. I would always favor bore size over stroke, just because if you go with a huge stroke, like your piston is moving at, you know, 500 miles an hour, it's just, I would always say bore over stroke, and just concentrate on RPM if you want to go that way. Obviously, if you're building a diesel caterpillar engine, that's not the way to go, but with high fidelity stuff, keep your stroke in check and lighten your parts that are moving. But so this is a forging of 2 series, I think 219 series aluminium. I can't remember off the top of my head, but 2 series. So it'll be forged first into a stamp and die, forged, get the grain structure right, and then machined afterwards. So you can see it's all post machined. You can hopefully see the tooling marks all over it, and then hand finished after that. So loads of tool marks there. These holes here then are lightning holes, and they're also holes that go all the way in there. They're I think 5.6 mil diameter, and they go all the way nearly to the crown, and they just lighten it up. And they also allow oil in there from the squirters down below, which is coming in a video soon, which should be out long ago, but it is what it is. So oil can spray in there and cool the crown. So they go all the way in, like really deep. So they go, you know, nearly to the crown. And again, these bridges here are just bridges. So if I put my finger in there, they're only about 8 mil deep. So they just keep this in check here. You can probably see it better like that. So yeah, that's kind of the underside of it. The clips, there's a lot of science in these clips. These clips are expensive. They are spring steel. They are, I think, €85 each just for the clips. Um, you know, you don't want them to come out at all. In terms of guidance in a Formula One engine, there's a lot of debate. It's you know, it's they're piston guided Conrods, because there's a jig of Cosworth as well to measure the end float here, the radial end float. When you have it all assembled, you put this into a jig with the Conrod in here like that, and you measure the end float, just because it checks the guidance. Um, so yeah, that's the underside, I think. Again, this is DLC coated. Now this has been ran in a dyno for a very brief amount of time, so you might see very light scratches there, but they're not. They're not. They're just what we call. Actually, you can't see them now, but they're very light. They catch the light sometimes. So you can see the DLC coating there, and the crown. So in terms of the crown, it's mirror polished, just not to pick up carbon. In terms of building the engine, which I touched on, I think in an earlier video, the crank throw would be measured, the conrod length would be measured, the piston would be then set in the block, or sorry, all the measurements would be put into a table. The piston would then be checked, and the squish zones measured with all the various stack up measurements from the discrepancies in the length of the conrod, like we're down to microns, the throw of the crankshaft, the distance of the small end pin to the top here would all be entered, and you would then send the piston to the machine hall to get the swish zones accurately machined once you've taken all the stack up into account. So very important, you know, and that's done for each one, not just a general over the whole cylinders or over the whole engine. So yeah, that's kind of that. Is there anything else? I don't think there is. Like, it's really light, very light. And just to check, so as you know, with pistons, they're not, what would I call them, cylindrical. So the skirt will be, again, these are random. Is this zeroed? No. So this isn't accurate, it's just for reference. So on the skirt, it's 97.75. Okay, so if I flip it and check the top here, it's 97.27. So that is because we've got a taper angle here and here, because this is exposed to the heat or the fire and will expand more at the top. So that's taken into account when it's been designed, and you've got a taper angle like that on all pistons. So when this gets up to temperature, it'll expand and it'll be parallel. So that's nothing new, but what is a tiny bit new, again, this is a billet item. It's not cast. Because it's billet, the billet will expand more than a cast item, because cast aluminium has more silicon in it, which keeps it more stable. Which any of you that bought pistons from Wassner or from GE or from whoever, you will know that a billet piston takes more clearance than a cast piston. That is just solely because of the chemical composition of the piston itself. Again, these are a lot tougher. You know, you could hit this with a hammer, it wouldn't break. I won't be doing that. But with the cast piston, because of the silicon content, it can fracture easier. So if you go turbocharged, you go with a billet piston or a forged billet piston, forged or billet, just because it's tougher and it won't fracture as easy, but it does require more clearance because it expands more because there's less silicon in it. So let's just check that once again, just to show you the taper. It's quite a large taper. So 97.77, okay. And if we flip it here, so 0.03, so that's a lot. Now if we flip it this way, it's different again. So 97.29, and if we measure it here, let's go this way. So here, so 97.48, 97.31, and 97.5. So I know what you're saying. Why is that? Because we've got all these features here. So as this heats up, it's going to expand more here because we've got double aluminium here and here than we have here and here. So it's going to expand more in this direction than this direction. So that's very easy to compute off the CAD. It's easily understood. So you end up with a this sort of shape when you're machining it. Now again, some pistons are round in this direction or in this axis, but the more high fidelity you go, the more not round they are, because you have to take into account all these are going to expand different in terms of thermal expansion. Again, like it's Formula One, it's not it's not normal stuff. So every tiny thing counts. So let's just pull that again there. So 97.76. And here is 97.26. And that is simply because obviously we're farther down the taper, but we've got more mass here than here, so it's going to expand different. So that's kind of that. The pin areas or the clip areas here are important. They give great instruction on assembling these. So you can see they're just a normal snap pin. Hopefully you can see that. This one is out obviously here. Just when you're machining them or when you're assembling them, not machining them, that they're deburred after machining, and there's no stress risers or burrs or anything like that when you put in your pin. So if we can assemble this here, let's just see where we are. One inlet. So normally with this is the Conrod is stamped here number ones. This is bank one number one, and it would normally be on the inlet side. So if we assemble this very carefully and just put in that pin here now, so that goes in there. So that's it assembled. So again, you can see the difference between this and what I will call a normal rod. So it's quite something, The rings, let's have a look at them while we have them. So again, I had TJ parts, which I hoped to do the video on instead, but it is what it is. These are CA parts. So this is the compression ring. Be very careful with these. As I said, these are viable parts that are going into an engine. So these are CRN coated. They're nothing, like looking at them, they're nothing special. The top ring is, let's just put a size on that. So the top ring is 0.6 mil thick. Now, generally, when you're sizing these, you've all done this. You close the ring like that, put it into the bore, and in a normal engine, I don't know what it is. Let's say it's 10 thousandths or something like that. In an F1 engine or in the CA engine, it's 1.5 thousandths, the end gap. So 1.5 thou is what you want that gap to be there. And again, there's strict instructions on how you deal with the chamfers on the ends of these. So on the top, the chamfer here, this way, you do have to chamfer it a small bit. So it'll be chamfered like that. So it's 0.5 mil in the X and the Y direction. And whatever the hypotenuse is after that, work it out yourself. But there is a chamfer that way, just at the top, facing up. Nothing on the bottom. And again, that's on both sides. So like this and like this. And there's also instructions here on this, the inner diameter, this edge here, and this edge here, just to round them over with 3M diamond paper. So that's the sort of detail that a top ring needs to be. Now again, in terms of clearance here, off the top of my head, it's 1,000 or less clearance. Now you'd never really have to worry about that. You know, you're not checking a worn engine. It's as they are, it's new parts. So you're not going to be running these like for 10,000 miles, but from memory, that's what it is. It's about 1,000. Now I don't want to fit the ring because there's a special mask here to fit the ring where you walk it on. I just don't want to mark the DLC coating because, as I said, these are viable parts. Let's go on to the oil control ring. Again, nothing too awful special. 3-part ring. You've all seen them before. So you've got your top and bottom ring parts, and you've got the separation ring, which is focus like that. So you know, standard enough. So they go together, they stack up like that, and that obviously you'd vary your end gaps. Everyone knows that. And the stack up then, just for laughs, we'll measure it. Just the overall ring thickness. So it's 1.98. So like, let's just say the groove is 2 mil thick. So that is that. Put them in again very carefully. So in terms of price, I've covered them before. I think the top compression ring is €180, I'm going to say. The oil control rings are cheaper. They're like 90, something like that. So yeah, they add up. Like, they're not, obviously they're expensive, but you know, if you just have to buy one, it's fine. But if you have to buy 8 or 10, it adds up fairly quick. And obviously there's a lot of other parts as well. You know, I guess the most demanding parts in terms of cost in a Formula One engine are the pneumatic valve systems, or the valves. Obviously the crankshaft, you'll be talking 25-30 grand, which is fair enough. But generally you can run the crankshafts, you know, a long time. Camshafts are fine. Conrods, debatable. They really need to be changed fairly often. Valves, definitely have to change them. The blocks, the sump girdles, they tend to be fine. But the valves and the PVRS, or the pneumatic valve system, all that sort of thing, they kind of need to be changed as often as you can afford. Some teams are different, but yeah. So hopefully that kind of covers the F1 Piston and Conrod. Obviously, I'm concentrating on these because, I think I've said it before, and I'm not going to make a habit of it, but like the V10 and the V8 F1 engines, naturally aspirated, they were the best. Let's face it, in terms of mechanical limits and all that. So, yeah, there she is. Um, as I said, I'm traveling to Monza on Friday night, Friday morning. I'm not sure. But I'll be there for the weekend, and there's a V10, a Cosworth TJ V10 running there. So I mightn't do a video. I don't know. It's tends to be very busy over there. But if there's anything crops up, I'll try and get out a video if I can. If anything needs to be fixed or something comes up, or just the general startup procedure maybe of the engine. So let's see how it goes. All right, guys. Chat soon, and thanks for watching.